as I said, thanks very much. You're welcome here today to this CPD. As discussed, we're kind of just going to have a look at the steps involved in the heat pump grant from a design and a documentation perspective. So kind of start to finish from a heat and design company's perspective, what information we would require from yourselves, the heat loss calculations, a bit about the heat loss calculations and where that information is used that we require from yourselves. We'll just also have a look at working out the outputs of existing radiators, because that seems to be a bit of a point of contention in the industry. We'd also look at then new radiator size and sign-off sheets, what the different bits and pieces in it mean, and who's kind of responsible for the various parts within it. And then we'll also just look at a case study of a completed heat pump grant job. So from where it started, the steps that were involved, the information that was provided and supplied, and how the job finished up. So I'll just briefly, the company, as noted, I work for is Grant Engineering. So Grant Ireland was established by Stephen Grant in 1978 in Birr. Grant UK was then established in 1996 and is now based in Swindon. And Grant France was established in 2018, which is based in Chambéry. We would export into a lot of countries around the world, predominantly outside of the three main bases: Denmark, Greece, New Zealand, Finland, Lithuania, Greenland, and more. We originally would have started off with solid fuel back boilers. We then moved on to oil boilers, then on to condensing oil boilers, and then maybe about 15 years ago or so, we had to move with the times into the renewables market. So originally then we would have started off with solar panels. And then we moved into wood pellet boilers. And then for the last 6-7 years, heat pumps. And in the last 3 or 4 years, we moved into a whole house solution package. So radiators, underfloor heating cylinders. So basically everything involved with the project. So we are a whole house kind of design consultancy as well. So we would do designs for new builds, retrofits, and everything in between. So I suppose first off, there are information that's required from the assessor. So we want to take a look at, from your perspective, the assessor. You have gone out and you have done your pre-BR work on and you've done your assessment on the house. You've seen where the house is. So in terms of what the existing HLI is, and then in, I suppose, in consultation with the homeowner, you discuss what works are needed from a fabric point of view to get it up to the required HLI. So once you kind of have your, I suppose, finished works BER at that stage, what we need as a heat and design company in order for to complete a full heat and design for that homeowner. So I suppose the first and foremost thing that we need when it comes to doing any sort of heat and design is we need a set of plans. Now, I know from a retrofit perspective, plans are not available. So a fairly detailed sketch is adequate. So once we can see the room layouts, the room names, and the external walls, and what rooms are adjoining each other internally, is good enough for us. So it doesn't need to be a full-on CAD spec drawn, but if we can get something as detailed as what's on the screen, that's ideal. So you will be doing your sketches on site anyway. So if them sketches are able to be provided, that is a great assistance to ourselves. We'll see as we go on. Sometimes a homeowner might just send in the dwelling report. Now, the dwelling report will give us a fairly accurate idea of the heat loss of the building, but we cannot work out anything got to do with the heat emitters from the dwelling report. So at that stage, all we could advise on would possibly be the size of the heat pump. So in order for a full, accurate heating plan to be done, a set of building plans are required. We also need the windows. So the windows are as important as the plans. A lot of the time you will just get a sketch and it'll be the living room, the sitting room, and so on, but you don't have any of the windows. And as we know, in the last 10 to 15 years, glazing has really kind of come on as regards sizes and so on. So like there are situations now where you have kitchens and living rooms and 70 to 80% of the surface area of the wall is taken up with glazing. So it's important that all the windows are measured and you have a full list of what's what rooms they're in, possibly even the orientation and the actual quality of the window. The existing radiators need to be measured on site. So in order for us to determine whether an existing radiator is good enough to be able to remain in situ or it needs to be replaced, we have to have that detail. So we need to know the size, the type, the spec of it. Is it a single panel? Is it a double? Is it a double panel, double fin, etc. So that sort of information is important to be recorded on site. We also, as noted, then need your post-works BER, so what that building is going to be from. So when the final works is done from an insulation perspective, because in order for us to do the heat loss calculations, we need to be able to extract the U values of what the house is going to be as opposed to what it is today. So all the information then that we can that we require, we'll be able to extract from your post-works BER, so from U value perspective, air changes, etc. So it is important. So I suppose just to summarize, the main things that we need to get from yourselves is we need your dwelling report, we need a plan or a sketch of some description, we need the windows, and we also need existing radiators. So if you can provide a heating designer with that information, that's everything that they will require in order to provide a full heating design, which will be compliant with regs and so on, that can be submitted to SAI. So they are the base requirements that's needed to get the process underway. From there, I suppose the main things with heat pumps and heat pump grants and actual heating in general is actual heat loss of the building. So the days of estimations are gone. So kind of guys looking at the room, oh, this size radiator will work here, or this boiler for there, or rule of thumbs, that's all out the window. So everything has to be done on a room by room basis. So full on heat loss calculations have to be completed in order to provide a full detailed heating schedule, which, as we'll see later, has to be uploaded. So it's crucial that it's done correctly. So this section will just have a brief look at actually the heat loss, what it is, the actual calculation, and where the information that you have previously provided is inputted and why it's important to get it. So basically, as you're most well aware, heat loss is the measure just of the total heat transfer through the fabric of the building from internal to external via either conduction, convection, radiation, or a combination of all three. Based on the second law of thermodynamics, heat flows from hot areas to cold areas. So most homes will be maintained in around 20 degrees internally. But as we know, the external air temperature changes. So once we have a change in temperature from inside to outside, we're going to have heat transfer through the elements of that building. They're predominantly nowadays measured in watts, but in previous generations gone by in BTUs. So the fabric heat loss is essentially the amount of heat loss through the physical elements of the building, such as your walls, your ceiling, floor, windows, etc. So the information that's required to calculate a fabric heat loss calculation is we need to know the internal design temperature, we need to know the external design temperature, you need to know the surface area of the specific element, and then you also need to know the U value of that element. So when we are designing a building or a retrofit, the element areas are generally set out by the homeowner requirements, or in, I suppose, the case we're focused on retrofits is they're physically already there. The temperature difference between indoor and outdoor is kind of set by the design criteria and the climate. So as kind of designers and heating engineers, so the only value that we can generally adjust is the U value. So realistically, we need to get the U value as low as possible in order to minimize our heat loss. Now my computer is froze. Apologies. Oh, here we go, sorry. So just the simplified formula then for heat loss is Q is equal to U times A times delta T. So Q being our heat loss, U being our U value, A being our surface area, and our DT then is our change in temperature. So everything got to do with heating is dependent on the change in temperature. So our overall heat loss through the building can be found in is the sum total of our U values times our areas times our change in temperatures. The second part of heat loss then is our ventilation heat losses. So ventilation heat losses are probably as prevalent as fabric heat losses, but in people's perception, it's not really a major source. So everyone can imagine heat loss through the building, so poorly insulated walls, or poor all insulated windows. But when it comes to ventilation losses, air changes, and so on, it becomes a bit more harder for people to comprehend. And then you'll also kind of get the discussion between a homeowner and installer, be like, oh well, you want me to seal up my house, but then you want me to put ventilation, or you want me to put fence in the walls and windows. But basically the difference is ventilation is a deliberate process of replacing air in a space to provide high indoor quality. And because of designed ventilation rates, we can account for the heat loss that's provided through ventilation. So we'll know that X amount of watts of energy will be lost over a certain period based on the ventilation strategy of that room or building. Whereas the air tightness or the infiltration is the uncontrolled ingress and egress of air into any space through air leakage points. So if the infiltration is unknown, we can't account for that heat loss. So that's why we need to get it as sealed as possible and then add our ventilation after, which we can account for. The CIBSE Heating Design Guide and NSAI SR 50 and 50-1 and 50-4, so domestic heating and plumbing and heat pump standards, provide us with set guidelines of our internal design temperatures and our air change rates for both new build and retrofit buildings. So this is where all our values will come from as regards our internal temperatures and our design ventilation rates and so on. The ventilation rates, although it may be set, if we see here in a new build, it's in a lounge 0.5 and a retrofit is 1.5. But once mechanical ventilation and different ventilation strategies are introduced to a building, then ventilation rates may change if the flow rates from the ventilation system are greater than what we have allowed for on the basic air change rate. So they can be adjusted. Generally on retrofits, you probably won't. Because I suppose full-on air tightness and ventilation systems probably aren't as prevalent on the retrofit. Also, then if there's chimneys or open flues or that, then the air changes would increase significantly. So I suppose from a heating perspective, it's important that if there was any open fires or that they're blocked, or else stoves with possibly central air installed just to reduce our air change losses. As regards the two air change factors, new build and retrofit, the new build one is effectively since kind of 2011. So if you have air changes of 7 or below, or possibly 5 in some cases, you would use the new build. And then if it's previous to that, or if there's no air test, you would use the retrofit or the pre-existing building standards. So you can have a retrofit, and if an air tightness test is completed, then we could use the lower ones, providing we get a total home value of less than 5. So just on the ventilation heat loss, so it is effectively, the calculation is 0.33 times V times N times DT. So again, Q is actual ventilation heat loss. 0.33 is the combination factor of the density of air and the specific heat capacity of air. V is the volume of the room. N is the number of specified air changes, which we would have taken from that previous table. And then DT obviously is our temperature difference between indoor and outdoor, which will be factored in from our previous table as well, based on the type of room. In Ireland, we take a design temperature of -3 throughout the whole country, so you could take that, that's a constant. Whereas if you were in the UK, if you're in South UK, you'd probably use -1 as your outside temperature, whereas if you're up in Scotland, you might use -7. But in Ireland, we just use -3 all over, so that'll be a constant figure. And again, then you can just see the total heat loss is the sum of the ventilations and the sum of the fabrics. So basically, one of the main things with heat losses is that every room has to be treated as separate. So it has to be a full-on room-by-room heat loss calculation. Each room treated as a box, so 6 sides for heat loss. Every room then will have its own specific design temperature and air change rate. So a bedroom will have a design temperature of 18 degrees and maybe an air change rate of 1, whereas a kitchen / living would be 21 degrees and maybe an air change of 1.5 or 2, depending on the conditions. So it's important then that each room has its correct values allocated, which then goes back to our plan that we receive originally. So unless the rooms are actually labeled and we know exactly what's what, we can't actually complete a proper calculation because of the varying factors that need to be applied to each room within the building. And then also, the heat transfer will only take place when there's a change in temperature. So therefore, if you have 2 rooms side by side, so if you have 2 bedrooms side by side and you have a party wall in between, both of them are designed for 18 degrees, there'll be no heat transfer through that wall, so that wall will then be excluded from your calculation. Similarly, if you're a 2-story building and if you have the rooms top and bottom that are the same temperature. So there's a couple of different bits and pieces. So here we just want to actually look at a sample room by room heat loss calculation, actually what it is, what information is in it, and basically how it's calculated. So this is just an excerpt. Everyone kind of would have, there's different software packages. You can do them longhand, you can do them various different ways once the methodology is the same. But this one is just an excerpt from the SAI heat loss calculator on how they actually do it. So that's the format they would use. That can be downloaded online. So as you can see, it is effectively broken into 3 sections. So at the top section, you'll have the room specific. So the name of the room, whether it's kitchen room, living room, etc., your design temperature, 21, 18, 20, or whatever it may be. Our design external temperature in this case is -3. So our temperature difference then is 24, so it'll be -3 plus 21. The ventilation section then comes next, so you can see then the values that are inputted, so our number of air changes, the volume of the room, the length, width by the height. Then we have our factors and we have our design temperature, so you can see then our total ventilation heat loss given for that room. Next, we move on to our fabric. So we have our floor, windows, doors, walls, ceiling, all the different physical elements. So you would do that all the way across. There are areas, so it'd be net areas as well. So obviously you'd be subtracting window areas and so on from walls. And we get a total heat loss then for that room based on that condition that we want to heat it at 21 degrees and the air changes in this scenario is 1.5. We also then at the bottom, you'll see there's additions. So additions then can be made up of thermal bridging, which will generally be just taken as the standard 0.15 unless it was provided differently. But in the vast majority of cases, it will be just, especially on a retrofit, possibly on a new build, if you knew that there was thermal bridging calculations being completed, you might be able to drop that to 0.08 or 0.04, whatever it may be. Then you'll also just have to allow for exposed locations. That's basically because air tests and air change values are done based on, I think it's at 50 km/h winds. It could be corrected on that, but if you were at exposed location, you have to allow for a higher rates of ventilation losses, and then also just a high ceiling. So if you have high ceilings, you have to allow for the stratification of heat because the thermal energy will reduce as the room gets higher. So then you get your total heat loss for that room. So that will be completed then for every room in the house across the board. So as you can see, that if we revert back to what we looked for originally, in order for us to complete that calculation, we needed a plan with the room names and measurements so that we could decide what the actual criteria was for that room. We needed the window sizes. And then we also needed the U values from your postworks BER. So all that information was required in order for us to complete this accurately. So just to summarize on heat loss, because we don't want to spend too much time on heat loss and how it's done, but it's effectively, in order to perform it, as we discussed, all that information is required: dimensions, windows, external walls, design room temperature, U values, air changes, and their external temperature. So this is probably a section that gets a lot of there's a lot spoken about, or there's a lot of issues that you probably will run into when you're doing heat pump grant applications, when your installers are sending back information, or if you're trying to upload information to DEEP and so on, as to what to actually look out for. So in this section, we'll have a look at existing radiators and how we actually calculate their outputs, where the information is coming from, and how you actually how you can derive it. So once you see in your DEEP manual, and then you'll also see on the designer sign-off form, I think it's on tab 4 about the guidelines, it says that if existing radiators are used, please refer to the 4 documents. So the 4 documents is essentially SR50-1, SR50-4, City Heat and Design Guide, and then there's also the heat emitter supplement to the heat and design guide. So I suppose it's a combination of these 3 or 4 if you count the 2 SR50s, but these are where the information has come from. The SR50s is kind of more of a guideline, but practically how to calculate them, it will be a combination of the domestic heat and design guide and then also the heat emitter supplement. So the heat emitter supplement is effectively a guide, and it has different types of radiators that would have been out throughout the years. So this is just a screenshot of the first type that came up. So it's saying that if you have a radiator that's similar to a Stellarad Super or Hullrad or Belcon, 40 mil wide sections, so that would have been there in the 60s, 70s, and 80s. This is the outputs of the different rads. So you can see that they had 3 types. There was a single panel, a double, and a triple, and then there was 4 heights given. So 300, 440, 590.
Barry, have we lost you there?
Green rad, or it was whatever it may be, then you could use the data from them. But if the radiator is unknown, that's what brand and model of it, then you would revert back to this. So there, as I said, there's various types of heights and types and outputs and so on. So what this supplement guide does is it gives you an output per 100 millimeter of radiator. So if we take example, so you go and you're doing your assessment, and in the living room, there's a 1600 by 300 mil double panel, and it matches this type and style of radiator and its age bracket. So then you can go and you say, right, it's a 300 high and double panel. So you can see from our table that that type and size of radiator would give 60 watts per 100 mil at delta 50. So that delta 50 is important when it comes to radiator. So basically that is mean water temperature minus the room temperature. So if delta 50 would have originally came from standard efficiency boilers. So if you would have taken, you had a flow temperature of 75 degrees and a return temperature of 65. So the average of that would have been 70 degrees. And then they take an average room temperature of 20. So 70 minus 20 is 50. So that's where the delta 50 comes from. So almost all radiator guides and catalogs and spec sheets, you will see the outputs that will be listed at delta 50. Some of the older possibly might see delta 62, and then maybe some of the newer ones that possibly be down at delta 30 and so on. But the one constant that you'll almost always see is delta 50. So that'll be important as we go on, once we want to start using non-defaults and incorporating them with heat pumps. But as we've seen here, so if it's 60 watts per 100 mil of radiator, so we have 1600 mil, so that's 16 sections essentially, so 16 times 60. So that radiator will give us 960 watts at delta 50. So essentially, if you were to just connect an oil boiler up to that, that's how much you would get. And obviously you had it ran at 75 degrees, but that's what you'd get, 960 watts. Now that's how you would calculate existing rad outputs. As I said, there's different tables based on the type and age bracket of the radiator, but they all follow that same pattern. You'll have a table like that, single, double, triple, the various heights that type of radiator would have been manufactured in. Obviously, you can see there they're kind of odd heights: 440, 590, 740. If you went to the next section on the emitter guide and it was rads maybe around 2000, you 601 kind of change. You can also then, in some of the more common ones, you'll see the outputs at 4, 6. So conditions then. So it's so
sorry, Barry, we're having a bit of a problem with your sound there.
Oh, sorry. Is this cutting in and out? Is it
cutting in and out, Barry? Yeah, yeah.
Sorry, no, just. Is it any better now, or is it still going? Or
no, it's okay there for now. Yeah, we'll let you know if it.
Yeah, if you do, yeah, thanks.
Okay.
I think it's a Wi-Fi thing. If we could cut the camera, maybe if it goes bad again.
Yeah, I'll maybe cut it now just to make sure. Anyway, but as we are now using heat pumps, we're not able to get them sorted. What output the radiators will have temperatures. So most heat pumps, standard heat pumps anyway, the max they can get to is a 55-degree flow. So we need to, at the very output there, look at how factor with combination of whatever your differential factor, a pipe connection factor, an enclosure factor. So the main one is what you would see a lot of the time would be your correction factors or so on for the various radiators. So essentially how that is calculated is it's the mean water temperature. So that's the average of our flow and return of our heat pump minus our desired room temperature. So say if it's a bedroom, it's 18 degrees or 21 in the living, etc. The catalog then, so that will be listed that. So if we've seen in our previous slide, the supplementary guide was given it to us as a DESI. So our catalog is what the actual output of that radiator is listed at. So this will predominantly be 50. As I said, in some situations, it may be 62 or 30, etc. So, and then that is all to the power of 1.3. Certain radiators, as we'll see later, will provide a coefficient, so maybe 1.27, 1.28, 1.29. But if that's unavailable, you'll take 1.3 as a constant. So if we just do an example, we have a 50-degree flow, 45-degree return. So our mean water temperature there is 47.5. We want to take it in a living room, which is 21 degrees. And the catalog output for the radiators is done at delta 50. So we can see that our F1, our differential factor for the radiator under them conditions is 0.438. So the output at 50-degree flow is just under 44% of what it would be at 50 degree, or at, sorry, delta 50. The second thing then is the pipe connections factor. So as you can see in the diagram, it's essentially, there's three ways of connecting up a radiator. You have TBSE, which is top and bottom same end. You have TBOE, which is top, bottom, opposite end. And then you also have bottom, opposite, ends. When the radiator is tested in the factory, it's done under the TBSE. So you can see the value is of 1. So when you see a listed output and we'll just say it's 1000 watts for a specific radiator, that's based on it being top, bottom, same end. You can also see then that once you move into the different piping scenarios, you can actually up the output or the output drops based on that's what flow pattern of the heat water through the radiator. I would say, without any scientific basis behind it, but I would say 98 or 99% of radiators that are connected are all bottom opposite ends. So there is a slight reduction in the output based on the catalog stated output, basically because if the system was not set up correctly, you have a possibility that the flow will come in and go straight across the radiator and doesn't actually circulate to 100% of the area of the radiator. So you just kind of have to make allowances for the pipe connections. F3 and F4 generally don't change too much. F3 being your enclosure, so whether the radiator is fixed on a plain surface, if it's concealed, if there's shelves over it, etc. But it's generally almost always going to be in a fixed surface, and the same for the finish factor, so the type of paint. But that's generally regarded to the way it's done in the factory, so it would predominantly be taken as 1. So there are your 4 values that go in to work out the total correction factor for that radiator. So previously we had worked out that after doing your survey, and in the living room there was a 1600 by 300 mil double radiator from that time period. So now we want to know, if we were to operate our heat pump at 45-degree flow, what is the output of that radiator and is it sufficient for what we need? So in this scenario, we'll take our 1600 by 300 mil double. We'll take a heat pump flow of 45 degrees, temperature drop of 5 Kelvin, bottom opposite end connections, and it's on a fixed surface in the living room. So we have calculated that the output at delta 50 was 960 watts. Our flow and return is 4540, so the average that is 42.5. And our room temperature is 21. So once we do our calculation of 42.5 minus 21 divided by 50 to the power 1.3, we can see that our F1 or differential factor is 0.334. So once we just substitute them back into that formula, we can see that our total output of 960 times 0.334 times 0.96, because it's bottom opposite end, and times 1 by 1 for it's on a fixed surface and it's the standard paint. Now that radiator is only going to give us 308 watts output. So as you can see, it's less than a third of the output of what it was at delta 50. So that's effectively how you would calculate the outputs of existing radiators. So you would do that then across the board in the house, but it's essentially, that is the formula and how it's done. It's relatively straightforward, and that would be repeated then for every radiator in the house. So when we were doing a heating design, so we'll just take that we've done our heat loss calculation in all the different rooms in the houses, and we have our full list of what the heat losses are for each room. So in this scenario, we have a kitchen, we have a bathroom and a bedroom. We have our 3 heat losses worked out based on the conditions and U values and so on. And we can see that we have 3 existing radiators. In the kitchen, we have a 1200 by 500 double. In the bathroom, we have an 800 by 600 single. And in the bedroom, we have a 1000 by 500 double. So using our heat emitter supplement guide, we were able to work out the different outputs of the 3 radiators. So we had 1788 in the kitchen, 768 in the bathroom, and 1490 in the bedroom. We want to run this system, so we have decided we want to operate at a 48 degrees flow. So this is where we want the system to be, and if this emitters work at this, fine. If not, we're going to have to adjust them, but this is going to be our design parameter. So based on that, we were able to work out our correction factor. So using the previous formula, so our 48 degree flow, 5 degree drop, so our 48, 43, we're able to work out our delta T's, and then we worked out our correction factor using the same formula. So now we can see what the output of the existing radiators are in them different various rooms. So in this scenario, we can see that a 48 degree flow, the kitchen radiator, the existing one, will only provide 707 watts, which is short of the 945. The bathroom will only provide 288, which is short of the 447, but the bedroom will provide 685 versus a requirement of 516. So we can see here now that our bedroom radiator can remain in situ. It doesn't require to be changed. So we will follow this down on all the various different rooms. So this is how we will work out whether existing radiators are suitable to remain or not, and what needs to be changed. At this stage now, we have worked out the heat loss of the room. We've worked out what the outputs of the existing radiators are. And now we can see we have a list of what radiators need to be changed. So now we have to add new radiators to the rooms. New radiators are, I suppose, easier dealt with because the information is available. You know exactly that it's a Stelrad or it's a Meisenrad or whatever it may be, and you will have spec sheets to match up. So you're just reading values from tables, essentially. All steel radiators will effectively come with an output chart like what you see here on the left. So it'll have the various heights, the type of the radiator, whether it be a single panel, double panel, etc., and just the outputs. Some of the radiators then will also come with a correction factor table, which you see on the right-hand side. So it can tell you for delta 21, that correction factor is 0.32. If it's delta 24, it's 0.383, etc. If that table is not available, then we can just use our previous formula, F1, F2, F3, F4, and we can work out the correction factor. So either or is fine, but it needs to be one or the other. So I suppose it is a bit simpler. Then you will just extract from your table. So in this scenario, we just picked out a 900 by 500 K2, and we want to work it out at delta 23. So we can see that it's at delta 50, it's 1344 watts, and our correction factor is 0.363. So if we were to use that radiator at delta 23, we're going to get 488 watts out of it. Similarly with aluminium radiators, you get the same. You'll get a spec sheet, and you'll have your outputs based on the various sizes. Some will have delta 20s, some will have all will have delta 50s, but some may have outputs at delta 20. That would probably be used on new builds where a lot of guys will just select delta 20 because delta 20 would cover say a 45-degree flow, which would be the kind of the standard on the new build where you need to be for compliance and so on. So delta 20 would cover you for all the various room temperatures. So the lowest being a bathroom, which would be delta 20.5. So some guys will just use delta 20 across the board to reduce on calculations. So you can see there the different outputs, and similarly then you'll be provided with the conversion factor table. So if we just take out a 15 section 580 high radiator we want to find out at delta 21.5. So our output is 1860 watts and our conversion factor 0.335. So our radiator under them conditions will give us 623 watts. At this stage then we can start looking at the designer sign off. So a lot of the times we would do it to sign off. Once we have a system designed, we would do the sign off to be able to provide that to the assessor or whoever's taking charge of the project for the homeowner. Say, right, this is the design conditions, and this is what needs to be done in order for the system to be submitted. So the designer sign off effectively provides the system details and the site specific information related to that job. It details the system itself, so the type of heat pump, size, the controls, the parameters, so what the settings are, what's the flow temperature, what's the return temperature, what are we setting the hot water, etc. I suppose a big thing is actually who the onus of the sign-off falls to. So in most scenarios, it is assumed that it's the heat pump supplier, but it's not. It's the actual person that designs the systems. So as we'll see, the bulk of information that's required in the sign-off is actually the heat loss calculations, the radiator size, and the flow temperatures, etc., which will be all dictated by the actual radiator system / designer, as opposed to who just supplied the heat pump. Because in certain circumstances, an installer may design up the system himself. He'll go to the heat pump supplier and say, all right, I need a 13 kilowatt heat pump. We'll supply that heat pump. And then a homeowner might come back 6 months later and say, oh, I need a sign off out to your heat pump, but we didn't design the system. So then there's lots of arguments and pointing fingers and putting heads. So it's important just to note that whoever designs the system is the person that's responsible for the actual sign-off sheet. In order to use non-default temperatures, I suppose, which is the crucial thing, especially predominantly on new build, because we need for compliance, we need to get flow temperatures as low as possible in order to get efficiencies up, so we can meet our EPC and our MPC and our renewable contributions, etc. So for us to use non-default temperatures, our full heating design has to be firstly completed, but then also has to be filled into the system. So as you can see here, just an example of a completed one, where you would have your room heat loss, type of emitter, the manufacturer, the model, the output. So that would be what we have calculated our output to be based on the conditions. So in this scenario, it was a 50-degree flow, and say in the kitchen, it was delta 29.5. So our radiator there, which is a 2 meter, 600 high, type 22, which would be double panel, double fin, under that output will give an output of 77 watts. So that has to be completed all the way down. If this is not completed, are not completed correctly to match in with the flow temperatures, then we're not able to use non-default temperatures. So it's important that this part of the process is done correctly. But if everything we've covered so far is done, then it's a simple input and exercise. So it's important that all the steps are followed along the way, and then we can input all this information and be able to provide it to yourselves. This, I suppose, is a section in the heating design tab came in maybe 2 or 3 years ago, possibly a bit longer now, and then this section followed. So this is effectively where our conversion factors come from and what the outputs are and what the actual type of the radiator. So it's effectively saying this is the radiator, this is the size, this is its listed output, this is its conversion factor, and this is what it's actually given us. So we can just see we have our delta T, we have our radiator make, our model, our dimensions, the heat output from the manufacturer. So that's your catalog output. So it would be from your delta 50, predominantly from our radiator spec sheet. There we list that is based on delta 50. So if we had filled it out and it was from a spec sheet with delta 30 or delta 62, etc., we'd fill that in, and then we'd fill in our conversion factor. So this is either after coming from the manufacturer who supplied it, or as we have calculated based on the formula we've seen earlier with the mean temperature minus the room over the catalog to 1.3, and then that works out what the actual heat output of that radiator. So what you see in the right hand side, though, 1777, that needs to marry back over into that what's actually fitted or filled in for that room in the previous slide. So once we have got to this stage, we have our heating design completed and we have our radiator exponent tab completed. So now we're able to prove that the radiators installed will match the heat loss based on the flow temperature we want to use. And here's kind of evidence behind it. So now at this stage, we can start using non-default flow temperatures. So in this case, we're using 50-degree flow. So this can be submitted correctly then to SCAI. So just have a look at a case study of a project that was done, the information that was provided, what was provided back, and then the kind of end result. So it was a 2005 built 3-bed bungalow. It was in reasonable condition at pre-works, HLI 2.12 and a BR of C2. It was being ran by an oil boiler. You can see there that the delivered energy at that stage, 24,500 units per year with 7 ton CO2 emission. So we would have been provided then from the technical advisor who was overseeing the project in conjunction with the installer, a detailed plan. So we had the full plan of the rooms, external walls, full measurements. Then we also had the plan which showed all the existing radiators, the sizes, the types, whether they were a double panel, single panel, heights, so on. We provided images with radiators just so we could physically see, because there's different types of double panel. You have the older version, which is double, which has just the 2 actual panels, but then you have double panel, double fin, which has the fins at the back in between. You'd also have double panel, single fin, etc. So images of radiators allowed us to make sure that what the outputs we were calculating were actually matching what was on site. And then we were also provided with the post-works dwelling report. From here, we were able to extract out what the U values were going to be once the system, the heat pump essentially was installed, so that we could get the calculations as accurately as possible, because if we hadn't the proposed U values and we were using the original ones, the system would be way oversized. It'd lead to running cost issues and performance issues for the homeowner. So Obviously, and then extra costs because you could be going to a bigger heat pump, bigger radiators, etc. So it was important to get the correct U values. From here, then we were able to complete the full room by room heat loss calculation, work out the existing radiator outputs, and then supply heating specification back to the assessor and to the installer. In this specific scenario, when the homeowner was doing the works, they decided that they wanted to upgrade all the radiators. So it wasn't a requirement that all the radiators in this specific project were upgraded, but to just, while they were doing the works, they wanted to upgrade everything and have a full new heating system from scratch. So you can see then we're able to provide what the heat pump was, the hank, what sort of control was required, and then a full list of the radiators, what was needed. From here, then, I suppose the process will be the pricing and so on from the contractor, who then completed the work. And then once confirmation was sent back that the schedule was followed, or if there was any modifications that we just had to adjust our calculations, we were able to complete then the full heating designer form. So because we had designed the system, we were responsible then for filling out this. So we would have filled out all the system details, so the test and standards from heating, hot water, what the system was designed to run at, the flow temperatures, the hot water, the control strategy, etc. We were able to fill in the system details on the radiators and so on. As you notice, just this system was done at a 50-degree flow. We would always try get it as low as possible. So in a perfect world, we would do it at 45, but just in some circumstances on a retrofit, it's not possible just because the radiator will physically get too big and wall space is at a premium. Predominantly, the issues run into is kind of kitchen areas and bathrooms. So most bathrooms from houses maybe built 20, 30 years ago, they may only have 600-700 mil allowed for a radiator, and there's units and baths and so on. So we kind of have to work with what we can. There's a bit of to and fro between say the designer and the installer, so what they can physically fit. And so in this scenario was a case that we slightly had to up the flow temperature to 50 degrees in order to get this the required radiators fitted, so that everything then could be certified and signed off and proved that the heat demands could be met. So we would have supplied back then the full complete heating designer sign off, all the different tabs. As it was a grant headed job, the installer had to physically sign the sheet. So the SAI registered installer. So the whole sheet would have been filled out, except excluding the actual signature. Then we would have supplied back in conjunction with it the radiator schedule, and then also the conversion factor tables that was used in conjunction with them radiators. We also would have had to provide then the eco design data for the heat pump, and also the product labels for the heat pumps and cylinders and etc. So everything that was required for compliance, and then also for the assessor to input into DEEP to determine actual heat pump efficiency. So as you can see then, once all the information was inputted into this project, the final HLI was 1.98. The design HLI then came in at 2.14, which came in just under the 10% allowance, which was, I suppose, ideal. You'll always find anyway that the designed calculations, so when we do our room heat loss calculations, they'll always come in slightly higher than the DEEP one, because we're taking X amount of individual rooms with different air changes and so on. So it'll always be slightly higher, but I suppose the key is to try to keep it within the 10%. If it is above 10%, then we'd have to just give verification in writing that all the correct principles and methodologies and procedures were carried out. But thankfully in this scenario, it wasn't required. As you can see then, based on the flow temperature that was used in this project of 50 degrees, the seasonal efficiency of the heat pump came in at just under 460% and 197 on the hot water, which we can see then is well inside the guidelines for where the heat pump system needs to be in order to claim the grant, which is 300 for heating and 160 for hot water, so it was well inside of it. This house then finished up, so it went from a C2 with a HLI 2.12 to an A1 with a HLI of 1.98. The A1, I suppose, was achieved via the installation of solar PV. So without that, it probably would have got to a B2, but there was very little fabric upgrades required. It was just basic attic insulation top up, and the HLI was able to be achieved. And the home then is full on, completed, all documentation submitted, commissioning forms, homeowner packs, and a quick run through with the homeowner. So the homeowner is happy with the system, it's operating as it should, all paperwork submitted on time, because all the steps had been carried over from start to finish. All the information was supplied that we required, and then because of that, we will supply back all information that the technical assessor required in order to submit his paperwork for the homeowner. And just, I suppose, to show why the flow temperatures, so that we need to get away from using default temperatures where we can, if possible. So in order for the heat pump to be as efficient as possible, we need to the flow temperature needs to be as low as we can physically get. So we need to get that as low as possible. 55, as we say, is the default, but ideally in a perfect world, you need it to be below that, because as we can see here, which is 2 examples of kerosene and electricity, with the current price of electricity being so high in relation to kerosene, that your actual final cost per kilowatt produced, like you really need an SCOP of 410, 420%. So once you start upping the flow temperature, so if you were to do it at 55, there's a possibility that that efficiency will drop based on the other parameters and factors involved with deep. So in order to make it cost effective going forward, that flow temperature needs to be as low as possible, now more than ever. 2 years ago, when electricity was at 16, 17 cents a unit, it probably wasn't as paramount, but unfortunately now where we are with the price of energy, it is actually crucial. So just always try push to get it as low as possible, and not to be using default flow temperatures where possible. So that's I want to thank you for joining, and hopefully I tried to just give a basic overview of the different steps involved from the paperwork and what's actually involved, what's going on our side, and why we look for that information and what we need to provide back to you. So I hope it was of some benefit, and my email is there, so if anyone has anything on that or in future, please email and we'll try to assist as best we can. So thanks very much.
Thanks very much, Barry. Fantastic stuff there. I know there are some questions popping in. Stephen, if you want to maybe just present a few of them to Stephen or to Barry.
Sure. That was a great presentation, Barry. That table at the end was very, very interesting, I would say.
Yeah.
I wonder, just thing that came to my own mind there, if you'd factored in the water production end of it, would it have helped matters much or greater?
Yeah, like I suppose it dropped slightly depending on the usage, but I suppose we try to keep a total SCOP at the year. It can vary it depending and then obviously what strategy you're using with the heat pump and what temperatures and that. So it can vary it a bit, yes.
So a couple of good few questions came in there for you, Barry, for Gareth O'Neill. He's querying the -3, I guess, as a starting point. So maybe you could kind of explain that to him a bit. He says, why has the external design temperature changed to -3? I've asked SAI for a long time to increase this outside design criteria. Maybe you could comment on that.
Yeah, well, I suppose as long as I'm doing calculations anyway, it's been selected at -3. As we said, across the water in England, it changes. So they use different ones, whereas here, for some reason, we don't. We use -3, whether you're doing a heat loss calculation in Wexford or if you're doing it in Donegal, whether it be right, wrong, or indifferent. It should vary because temperatures will vary as you move up and down the country. But I suppose we have to just take from SR50, and what they stipulate to us is that we have to use -3 throughout the country. So like ideally it would be changed to have, north, south, slightly higher up in the north, slightly lower down south. But as we say here today, unfortunately that's what we have to use no matter where we are.
Absolutely. I know Wayne Moorhead Architects and a few people have done some work on this, and they've shown the huge difference between Belfast and the south of Ireland and West Cork.
Yeah,
And we all have to assume we live at Dublin Airport for now, I suppose.
this is it.
Yeah. Somebody also asked, where can they get that supplementary table for the rad sizes? So that kind of default table for the rad sizes. I
Yeah.
actually done a bit of Googling. Maybe you could throw a link in there for us or something.
Yeah, would you believe I was being asked over the years, I kept seeing this and assessors kept asking me where could it, and I, for love nor money, could I find it? I could find it nowhere. I got onto Sibsy, who create the heating design guide. They couldn't help me. So I eventually got it from SEI, but I will send on the link I have for it, and I'll send it to one of the guys there. And if they want to circulate it to everyone in attendance, it's just a downloadable link. So I can send that on to you.
Perfect, great. And just some kind of houseworky stuff here in terms of Barry share his presentation. You already said you would, Barry.
I will, yeah.
That heat loss table from SEI, I've shared that link in the chat. So if you scroll up through that, you can find it. Susanna Barry asked 2 questions. She asked, what type of rads are best suitable for heat pumps? Aluminium with high output, she suggests.
There was an initial train of thought a few years ago that aluminium was the way to go, but I suppose studies have found that it doesn't really matter. Once you have your outputs done correctly for that lower flow temperature, it really doesn't matter. I suppose sizing is key. I suppose some train of thought has been shifting towards back towards steel because you have a greater water volume. So an equivalent steel and aluminium would have 30% less water volume. So that was originally why it was thought it would be more efficient, because it was using less energy required to actually heat the radiator. But as we kind of come to learn that with short cycling and system run times and so on, that larger volume is more beneficial. So my answer is it doesn't really matter on the grand scheme of things, providing that the actual sizing is done correctly and they're tailor-made to suit that specific project. But one shouldn't really be, when everything else is factored in, so say control, amount of TRVs and stats and so on, that'll have more of a bearing on how well the system works than the actual radiator. But once both are done and sized correctly, there's not much of a difference.
Good. Martin asks, can a technical assessor sign off on a heat pump installation if they've done the heating design? That's what that ties in with Mark's question a bit further down. Yeah. Who normally does the heating design? Is it done by a technical assessor at an additional price, he suggests? I'm sure it would be Mark. So I suppose who does it, and can a technical assessor sign off on it?
If it's a non-grant aidable one, yes. If it's a grant, if someone's looking for a grant funding, the person that signs off has to be the SEI registered installer. But if it's a new build or just a private client that's not doing or not claiming funding, then yes, they can sign off on it. The heating design, I suppose this is where a lot of it runs into, is that, say for the likes of ourselves or other companies around, we would do it, but say if an installer takes it upon himself and he just goes into his local merchant and purchases a heat pump and the proper design is not done, we've always advocated that it probably should be the assessor that's doing it, and it should be a service that you charge for, because at least then you're in control of the system and are in control of the project, that when the client comes back to you and is looking for paperwork to be submitted, that it's done correctly and you know it's done and everything is there. Obviously it's a lot more work for yourselves, but the installers are not doing it, and they're not really cut out for it, and they don't have the information, or they don't really take the time to learn how to do it. So realistically it should either be a heating company like ourselves or the assessor that's doing it, and obviously the assessor charging for their time, not if as they should.
Yeah, I agree. Yeah, generally, I guess the people on the ground installing the actual equipment don't generally have that expertise or the time, I think, or the want to learn how to do it. I guess you need a backroom team. And yeah. James says that some installers won't sign off an SEI installer sheet. I guess it's the same thing, isn't it? Having to default it. Is there any way around that? Well, I suppose go back to your supplier. You'd suggest, isn't it? Go back to where the heat pump came from.
Yeah, so just follow back the chain of events, like as to what happened, like what was the procedure. The assessor, you done your assessment, you gave it to the homeowner, and you'd have to just figure out where it was taken from there. Did they just go in and purchase a heat pump based on your dwelling report? As we said earlier, that should be able to estimate the output, but then that has nothing got to do with the emitters. and just see where it fell down. I know it's a very, very, very tricky one, and you're putting an awful position, because if you have to turn around then and tell a homeowner, oh, sorry, no, you're not eligible for the grant aid. What you'll find is no one will take ownership of it. So the installer, oh no, sure, I'm only the installer. The homeowner will say, well, I'm the homeowner, and everyone will be pointing fingers. So it'll always fall back on either the assessor or the heat pump company, which is not the way it should be, because if proper procedures were put in place, you wouldn't have that issue.
Absolutely. I think, anybody getting a heat pump installed, I'd make sure that they had the backup supply of a company that would be able to at least fill in the sheet, never mind look for parts or something goes wrong. So I think you need that kind of backup service as a minimum. Somebody's asking about the full time and temperature zone control with heat pumps. I know this is something that's changing as the technology changes, I guess, that we're not seeing as many room thermostats, or we're seeing systems without them. So
Yes,
how do you justify it in an audit, I guess, is what they're really getting to, if
yeah.
there's no room thermostats visible?
Yeah, see, the problem is, as you know, all the control that's in deep has been designed and has come from oil and gas. So it's TRVs everywhere, it's thermostats everywhere. It has, it's controlled to death. As the industry has found in the last few years, that control is the actual enemy of a heat pump. So a heat pump, if you had it operating at lower flow temperature all day long, it's far more efficient than if it's been called on and off in short periods. It's short cycling. It's one room down the hall is calling, and so on. So it's something that SEI are going to have to upgrade sooner rather than later, because it's going to get to a stage now where you're going to have no thermostats in the house. That's the way the heat pump technology is going. The system will just operate on pure weather compensation, so it'll operate effectively 24/7, but it'll be far more efficient, because it might only be sending in 15-degree water or whatever it may be, and it'll reduce all the cycling and that sort of thing. So it's an issue for SEI. It's something the Heat Pump Association are in consultation with them about it, because it is, as you know, anyone that's been doing assessments for years, that control strategy is the same as it's been for donkey's years. So it is something that needs to be changed. I suppose at the minute, your beer, what you can get away with is one programmable stat per heating zone, and then your hot water. So I suppose that's what you need at the bare minute to get through. But it's something that's going to have to be looked at and changed sooner rather than later.
There is a caveat in that, though. That's only up to a certain house size. I think it's 130 square meters. Above that, you need a second space heating zone.
Or sorry, that's per zone,
yeah. Just a couple of things. A couple of things that struck me. Have you done any work on the actual performance of heat pumps in houses, particularly with ones with the HLI that come in around, the 2 mark, bearing in mind that the 2 could be generated generally by default values based on maybe the lack of evidence around the actual U values, etc. And similarly, in terms of flow temperatures and the like, simply the flow temperature entered into deep may be entered in simply because the information isn't there to substantiate anything other. But at the same time, the heat pump would be operating far more efficiently. And it ties into the earlier question of why the -3, because a heat pump in Wexford may perform much better than it may in Donegal, for example. Has there been any kind of real life studies done by the Heat Pump Association or yourselves internally, or anybody?
Yeah, there's lots actually going on at the moment there. So what was LIT and AIT, so is it TUS or University of Shannon? I know they're doing lots of research at the moment. We're doing a lot of testing with them. Tipperary Energy Agency doing a lot of testing as well on actual real life performance, and kind of relating back to that zoning and amount of control and flow temperatures and bits and pieces. So there is lots of information there. I should have something there that I can send on, so you'd actually able to see real life testing and how the systems are actually working based on real life applications.
And just one other thing, from our discussions with SEI, the HARP database is now enabled to accept heat pumps.
Yes.
And they are saying that the heat pump providers are slow to get their information onto the database, that there seems to be a delay there. Have you any insight into it?
Yeah, well, I suppose one of the reasons is that once it's uploaded, it can't be re-uploaded. So if you, so say a heat pump company, that if they know that they're retesting, or if they're changing a model, or if their property of the tank that's tested with is changing in the short to medium future, then they're holding back because they're not able to re-upload the system. So they're waiting until they have the final data for it to go up. But that's my understanding as to why some companies are a bit slower than others to get the information up.
Yeah. Okay. Is that all the questions?